Okay, welcome back. And today we're going to talk about the correlation coefficient. So last time we talked about scatter plots and how scatter plots are a visual way of looking at seeing if there's a relationship between two variables. And we talked about the strength of those relationships, whether they're weak, moderate, strong, if it's linear or nonlinear. And so there's things that we can see from the scatter plot, but they can be misleading, right? They're subjective, right? So we need a numerical value, some quantitative value that we can use to measure the strength of the relationship between two variables once we think there is one, okay? And so that's where the correlation coefficient comes from. So it was developed by Carl Pearson in the 1900s to measure the relationship or the strength of the relationship between an independent variable x and a dependent variable y. And so just to give you an idea of the correlation coefficient calculation, it's this monster right here. So again, we're not going to deal with calculating that. Our calculator is going to give us R, and I'm going to show you how to set up your calculator so that it will give you R when we need it. But that is the calculation for the correlation coefficient that measures the strength of the relationship between two variables, x and y. Okay, so now, here is the idea of the correlation coefficient. So here's the properties that we want to keep in mind. So the correlation coefficient is based on the number of pairs. So in this case, n represents the number of pairs. Okay, so I'm going to read off some of these. So again, if you want to pause and take notes, that's fine. So here are the things about the correlation coefficient. I'm going to write some of this down, but some of it you're going to have to take notes. So it's one of the things is that the correlation coefficient is on a range of a scale. So it goes from -1 to +1 and anything in between, so including 0. So R is on this scale of values from -1 to +1. And so now, a positive value of R means that it's a positive correlation, right? Makes sense? A negative value of R is a negative correlation, right? So that's based on what we were talking about earlier. The sign of R is the same as the sign of the slope of a straight line, okay? So again, we're going to talk about that later, okay? So the way this works is if your correlation coefficient is close to 1, let's say around 0.7 or higher, okay? Or if it's close to -1, let's say -0.7 or lower, okay? Then we might say that that is a strong correlation, okay? Now these are rules of thumb. Now if you're around 0, right, let's say -0.3 to +0.3, okay? So let's say you're around here, then that would probably be weak. I mean, if you're really close to 0, then there's no correlation. So 0 means there's absolutely no correlation at all. If you're around any in this range, you might be a weak correlation. If you're anywhere close to either +1 or -1, that would be a strong. And then of course, anywhere in here, around 0.5 and -0.5, we might say that that's moderate. Okay, but again, these are just rules of thumb. It changes from industry to industry. I've worked with data where correlations of 0.6 were considered strong. Okay, so again, it's based on what industry you work in and expert opinion. So just keep that in mind. So we're going to stick to just these rules, rule of thumb, this rule of thumb here. Obviously, if you're at a -1, that's a perfect negative correlation. Or if you're at a +1, that's a perfect positive correlation. You're never going to see that in the real world unless it's just a mathematical formula. But just keep that in mind. Let's see, R is the same no matter what units are used. So this is a unitless number, right? So it doesn't matter what units X and Y are in. Typically they will be different units, right? Because we might be measuring inches versus pounds, okay? But it doesn't matter because those units will all drop out at the end. Okay, so it's a unitless number. So it doesn't matter the units. It also doesn't matter if you switch X and Y. So if you make the X variables Y and you make the Y variables X, it doesn't matter. You're still going to get the correct number. Why? Because the units drop out anyway, right? So it kind of follows from what we just said. Let's see here. Now, main thing here for R, okay? Correlation. So this measures, this is the correlation coefficient. So it measures the strength of the relationship. In fact, it only measures the strength of the linear relationship. So R only measures linear relationships. So it cannot be used for nonlinear curves, or, well, that's the same, nonlinear patterns, nonlinear relationships, okay? So keep that in mind. If you were to calculate R on a nonlinear relationship, it would be very close to 0, okay? So, and that should make sense. The other thing too is to remember this. Just because you get something that's either very close to +1 or very close to -1, just because you get a very strong correlation, okay, does not mean that one variable is causing the other variable to happen. If one variable is going up and the other variable tends to go up, and you calculate the correlation coefficient and you find that it's very high, positive, that doesn't mean that the one variable going up is causing the other variable to go up, okay? So keep that in mind, and the main thing is the phrase correlation does not equal causation. So remember this phrase. Correlation does not equal causation. Meaning, just because two variables are closely correlated, okay, and that there's a strong relationship between the two, does not mean that one is causing the other. We talked about that back in chapter 2, I believe, chapter 1 or 2. Okay, so in order to prove or demonstrate that one variable is causing the other, we would have to do an experiment. Okay, so just be aware of that. Okay, what else? Let's see here. Let's see. Oh, so here's how we're going to do the correlation. Now, let's see here. Okay, let me find some data. We could do this. Okay, so we're going to use some data, and we're going to calculate the correlation coefficient. So the first thing you want to do is we need to put your calculator and make sure your calculator is set up right. So we need to turn your diagnostics on. Okay, so if you have a T83 or T84, what you want to do is you want to go to your catalog. Okay, and the way you get to your catalog is you're going to do second 0. So you're going to hit the second and then 0 key, and that's going to bring you to your catalog. Okay. Once you're at your catalog, then it gives you a menu of all of the functions in your calculator. What you're going to do is you're going to want to hit the D key for the letter D, because once you get to your catalog, you're going to be in the alpha mode, okay, which means you're using the letters. And if you notice at the top of each key, some of these keys here, you're going to see that some of these keys have a letter in green, like there's a T, U. So what you want is you want D, okay, where D is right here above the inverse key. So you want to do, just hit the inverse key. You don't have to hit the green because you're already in alpha mode when you go to your catalog. So just hit your inverse key and you'll go straight to your menu. So if you go to second 0, right here, it's going to, oops, sorry, need to turn on. So if you do second 0, now I'm in catalog. Okay. Now all I have to do is hit my inverse key, so hit D, and now it brings me to the D's. Now if you scroll down, you're going to want to scroll down until you get to diagnostic on and diagnostic off, which is right there. So I'm going to highlight it. Okay, come back up here. So if you go back up, see how the arrow, now I'm on off. Now you want to go to diagnostic on and then hit enter. Okay, so if you hit enter, you're going to have, hold on. Now if you hit enter, you're going to now go to this screen here and you'll see diagnostic on at the top of your screen. Hit enter again and now it says done and you're done. So your diagnostics are turned on now, and they will stay on forever unless you turn them off. So now we can go on and calculate R. Now notice also, one thing I want to talk about before we do that is R is the sample correlation coefficient. It's the sample statistic. So R comes from the sample, okay? So if we have a sample, we can calculate R. If we have the population, then we can calculate rho. Rho is the Greek letter that represents the parameter, the population correlation. Which means that, hey, if we were able to take all possible pairs of XY from the entire population and then calculate the correlation, that would be rho. So again, we don't know this most of the time, very rarely. So R is based on the sample, okay? So just be aware of that, because when we get to the hypothesis testing, we're going to compare to see if it is a significant R value. Just because we get a high R value, let's say 0.97, just because that's a high R value, it tells us it's highly correlated, but it doesn't mean that's automatically significant, okay? Okay, so now, let's use this data. Okay, so here's the data. We have age and pressure. And so what do we want to do? We want to find the correlation coefficient for 9 randomly selected adults, and we want to find the correlation coefficient between their age and their systolic blood pressure. So here's the age. And here's the systolic blood pressure. And I'm assuming this is in milligrams of mercury. Okay. So now, what are we going to do? Well, we're going to put one list into L1 and then one list into L2. So let's do that first. Okay. So I'm going to go to Stat Edit, and I'm going to put in my age group, my age list into L1. And so there are my 9 ages. And so now I'm going to put in the blood pressure. Okay, so now I've got them both in. And now I'm going to quit out of this. And now what I'm going to do is I'm going to go to my Stat Calc menu. Okay, so now we're going to go to Stat Calc. Okay, and under Calc, we want to go to number 4, which is linreg and it's AX plus B. We'll talk about that, AX plus B, later. Now, when you hit linreg, so here I'm at linreg, okay, and here I'm going to get that at the top of my screen. Now all I have to do is put in L1, comma, L2 at the end. So that's what I'm going to do. I'm going to do second 1, comma, second 2, and now this is what I have. Okay, so now because I need to tell the calculator where my X data is and my Y data is. Okay, so then when I hit enter, now it's going to give me all of this information. Okay, some of it we're not going to use right now, but notice at the bottom it says R, and R in this case is 0.9597, so or 0.960 if you round. So in this case here, R is equal to 0.960. So really high R value. Okay, very close to a positive. And as you see, look at the data. As age is increasing, I mean, every single one is increasing. So it makes sense that this would be a strong positive correlation. Okay. Now the question is that a significant correlation? Okay. That's where our hypothesis test comes in. Okay. So now at this point, you know how to calculate R. Okay. Practice doing that. Okay. You could take the other data sets. You can take any data set as long as you put in your X value and your Y value into different lists, and then just make sure you go through the steps that I just did, and you're going to get R. Okay, that's the easy part. Calculating R, that's, you know, just doing this, right? So now the other thing too is start thinking about which one should be your X value and which one should be your Y value. Remember, normally Y is the dependent variable, right? Remember in linear, you know, anytime, even when you've studied straight lines, algebra, whatever the case may be, a straight line has this equation or this form. Okay, where m is the slope and b is the intercept. But the main thing I want to look at is this, the x and the y. X is what we call the independent variable, and we talked about this in chapter, what chapter was that? There was chapter 2 when we did experiments, or chapter 1 rather, and we were doing observational studies and experiments. So here, X is the independent variable, right? y is the dependent variable. Y, when it comes to this guy, we want to make sure it's whatever we're trying to predict, and we're going to talk about that later, but y, you want to make sure you pick y as the dependent variable, the one that depends on x. Well, which one depends on which one? Well, blood pressure depends on your age, right? So blood pressure, it seems like, depends on how old you are. Now, it doesn't make any sense to say, well, age depends on blood pressure. Does that mean that if I measure somebody's blood pressure that, well, I can predict how old they are? No, not necessarily. Then we wouldn't want to do that. That'd be kind of ridiculous because we can just ask them, how old are you, right? So, but if we say how old, if we find out how old they are, maybe we can predict what their blood pressure might be without having to do any blood tests, right? So now, so in this case here, this would be our x variable, y would be, or excuse me, pressure would be our y variable. So age is the independent variable, y is the dependent variable. Okay, so why do I say that? Well, because it's going to be important later on. Not for correlation coefficients, but later on when we get to regression. Okay, so now, how do we test this, right? So we got r is 0.960. So what? Well, let's do a hypothesis test. And the hypothesis test that we're going to perform is a test for correlation. And this is going to be a very simple hypothesis test because it's always going to be the same. So step one is going to be that rho is equal to 0, meaning there is no significant relationship between the two variables. Where have we heard that before? Isn't it the same as independence? Right, so if we could look at this as independence too, right? Are the two variables independent? But let's just stick with the correlation. So is the correlation 0, meaning that there's no significant relationship between the two? Or is rho not equal to 0? Okay? That's the question. So it's always going to be a two-tailed test. Okay, you could do a one-tailed test, but for our class and for our purposes, we don't care the direction of the correlation. We just care whether there is a correlation. Okay, so in that case, it's going to be a two-tailed test. And of course, step 2, we're going to always assume the null is true. So we're going to assume that rho is equal to 0. Okay, now, in step 3, we're constructing hypothesis testing for this, and let me see something here. We're going to take our data, right? So we're going to have our x data, and we're going to have our y data. And so we're going to put our x data here, and this is going to go into list 1. We're going to put our y data here, and this is going to go into list 2. Okay? And then we're going to have our alpha level, right? Now our alpha level will only be 0.01 or 0.05 for these. Okay? 0.0, so that's going to be either 0.01 or 0.05. Okay. Now, the test. There's a couple ways we could do this test. Okay? So when we do the test, we can use this test statistic, which is a t statistic. So when we do the test, we can use t star is equal to this. And it's going to be r, based on our sample, r times n minus 2. So n minus 2 degrees of freedom. Why? Because we're dealing with 2 samples. So it's n minus 2 divided by r 1 minus r squared. And then what we could do is we could check this against our T alpha, okay, or actually T alpha divided by 2. So we could do that by hand, right? So we could use the T table, right? Or we could use inverse T to get this critical value and then compare the two, okay? That's one way, okay? The other way is to take our R value, right? Which we're going to do, so here we can do ln reg AX plus B, right? And we can get our R value, right? Well, and then we can compare that to the critical value on the correlation table, which I'll show you right now. So if we look at this correlation table, oops. So now this is just an example, okay? Not the one that we have on Blackboard, but so here's an example of a correlation table. Okay, now this one here is for an alpha level of 0.05. Okay, so this is strictly at 0.05. And it has the degrees of freedom. So notice that for the degrees of freedom, and this is for an alpha level of 0.05. So this whole table is only for an alpha level of 0.05. And so if you go down the degrees of freedom, you'll see that these are the critical values. Okay, so what happens? Once you find your critical value, the way the test works is this. Your comparison is going to be, is R greater than your critical value? If R is bigger than your critical value, then you're going to reject the null. Okay? And so if you reject the null, then there is strong evidence to support that there is a significant correlation between the two variables. Okay, so that's one way of doing it. Okay, so you could put your data into L1 and L2, your X and Y. You could use ln reg on your calculator and calculate R, and then check R on the critical on the table. But you must obviously you need to know the degrees of freedom, right? And you need to know your alpha, and it's either going to be 0.01 or 0.05. Okay. So that's one way. The other way is to use the calculator and to use the T statistic, right? So again, let's go back to this T statistic here. But we're going to use the calculator. So I'm going to write it up here. So T star is equal to R times n minus 2 over 1 minus R squared. Okay, now, we can do a t-test, and we can just do in the calculator instead of using the table, right, or the calculator. Okay. Again, the degrees of freedom is going to be n minus 2. And you need your alpha level, right? So again, you're going to use alpha. Okay, so do I have that? Yeah, it's a little low. Let me rewrite this. A little high, I mean. So let's do T star equals R times n minus 2 over 1 minus R squared. And then you have your T alpha divided by 2 that you're going to use. And what you need to know for that is you need to know alpha, and you need to know the degrees of freedom, which is n minus 2. Okay, so you're going to need to know that. But on the calculator, this is what I would use. You can use ln, oops. Ln reg t-test under your stat test menu. Okay, so under stat test menu, if you scroll all the way down, you can get to ln reg t-test. If you do ln reg t-test, not only will ln reg t-test give you R and a bunch of other stuff, but it's going to give you pretty close to the top, it's going to give you your T star value, and it's going to give you your P value. And so then once you have your P value, then all you have to do is just compare it to alpha, and you're done. So that's it. That's really all there is to it. So let's do an example. So let's use that example that we just did. Okay? So now, so here we are. So we're going to use this data right here. So again, what was our R value that we got? Our R value was equal to 0.960. So we're going to test here whether that was significant. So we're using the data that we just did with the age versus systolic blood pressure. So now, we got 0.96, but is that really significant? Well, let's find out. Well, if we calculate this, well, what was the N value for that? That was 9, right? So that means the degrees of freedom would be 7. So if we look at the table, right, what's the critical value for degrees of 7 at a 95% confidence interval? Well, for 7, it's 0.666, right? So here, if we did this method right here, instead of the ln-reg, if we did R is equal to 0.960, our critical value is 0.666, well then R equal to 0.960 is definitely bigger than our critical value, which is equal to 0.666, and so we would reject the null, and we would say that there is a significant relationship. So the 0.960 is significant. So that's one way, right? Well, let's use ln-reg t-test. So what I'm going to do is I'm going to use ln-reg t-test, and I'm going to put in L1 and L2 in there, okay? So now, here's what's going to ask you when you do ln-reg t-test. So I'm going to turn it on. So I'm going to go to stat tests, and I'm going to go to F, which is ln-reg t-test. And now it asks me for my X list. That's L1, already got it in there. Y list, which is L2, already got it in there. And then I'm going to skip frequency, we don't play with that. Now, the next thing is row. Now, what is row? It says beta and row. Don't worry about that right now. That is going to be your alternative hypothesis. So we're saying row is not equal to. So we're going to select not equal to. Now, the regression equation, we're going to talk about that a little later, okay? So now calculate, and now at the very top, so notice at the very top, or it's closer to us, says T is 9.03, and right below that is the p-value, which is 4.16 times 10 to the negative fifth, okay? So now we get T star is equal to 9.03, and our p-value, which is equal to 4.16 times 10 to the negative fifth, which is equal to 0.00004. Okay, so now we've got our p-value, and so now we can just use the p-value method, which is obviously much, so our p-value is definitely less than alpha, okay? And so, again, we're going to reject. Now, the t-statistic is the same t-statistic that you would get from here. So let me just quickly do that, just to prove to you guys, prove to myself that it is. So if I go 0.960 times the square root of 7, because it's the number of ordered pairs, minus 2, so 7, second. 7 divided by 1 minus 0.96 squared. And I got 9.07. So slightly off, but because we were rounding here. But close enough. Okay, so it works. So that's how we do a test for the significance of whether, a significance of correlation. So just because you have an R value doesn't mean it's necessarily significant. It may seem like it's significant, but the only way we know that it's a significant correlation is to do a hypothesis test. So other than that, that's about it. I hope that made sense to you. And again, review this if you need more practice and do some of the examples in the textbook or on the PowerPoints. And next time we'll talk a little bit more about correlation and we'll start getting into regression. And we'll talk then. Have a great day.